Today we're going to cover measurement very briefly, and we're mostly going to focus on significant figures. Measurement will cover quite a lot in the lab, so just some basics to understand going forward. When we want to measure mass, which is actually something we're going to be measuring very frequently, we use a balance. Very often you might have used a triple beam balance or even an electronic balance. Our international system for this that scientists use all around the world is the gram. Please keep in mind that mass is not the same as weight, so it's nice to begin to kind of think about those as two different ideas. Weight, remember, is including force of gravity, whereas mass is actually a direct measurement of the amount of matter that you have. We're also going to be measuring volume quite frequently. Very often we'll do this with a graduated cylinder, which you've used before, or something called a burette, which you'll get introduced to this year. Our SI unit is liters, but very frequently in chemistry we use milliliters. Milliliters are smaller, so they kind of go along better with the quantities we measure. Milliliter is really the same unit as the centimeter cubed. So when you hear about densities being in gram per centimeter cubed, that can also be expressed in grams per milliliter. You may remember that unit from earth science. Temperature is the last thing we're going to measure, and this is measured using a thermometer. Our SI unit for temperature is degrees Celsius. Also, sometimes we're going to be using Kelvin this year. Kelvin is important in certain types of calculations. We don't have thermometers that measure it directly, but it's extremely easy to convert. We do not use Fahrenheit. By being able to measure these quantities, we can determine things like density. Density actually combines mass and volume. Concentration is a measurement of a mass of a solid in a certain amount of liquid. Solubility relates the amount of something dissolved to temperature. Melting and boiling point also involve measuring temperatures as well. Something that's important to keep in mind when we are measuring is that we're actually reporting numbers that we can be pretty confident about. So the type of equipment that you use really limits how many decimal places, for example, you might have in a reading. So we're going to talk about something called significant figures, which scientists use to ensure that they are telling other scientists about things they have accurately measured. Very often when you do calculations in science, you get an answer, and a question I frequently hear is, how many decimal places should I have in my answer? Well, significant figures are going to answer how many decimal places you should have in your answer. So let me give you a little example of this. If I put a battery on a triple beam balance, and that triple beam balance told me that that battery weighed 2.3 grams. I can read to the 10th place on our triple beam balances. So I can be pretty confident that this is 2.3 grams. I can't really put any more numbers up there because I can't read them on the balance. If I put a film canister on an electronic scale and find out that it weighs 0.96 grams, I can actually read both of these. Our electronic balances here allow us to go to the 10th place. So they do allow us to, to the 100th place, they do allow us to read 2 decimal places. So imagine if I knew those two masses and I wanted to add them together. So I'm adding 2.3, 2.96. Which gives me 3.26. The problem that I'm running into is I have a big question mark here. That could be a 1, that could be a 9, that could be a 0. So that means that I can't be super confident that this is actually a 6. So I can't really tell people about that number. What I actually have to do is just stick with my 1 decimal place that I'm very, very confident of. So I'm going to actually change this into a properly reported answer with the correct number of significant figures. Since I don't know that that's a 6 for sure, I'm going to just round my 2, just like you rounded in other classes, and report my answer is 3.3 grams. So that way I'm not really taking a guess as to where this arrow is right here. I'm just kind of saying, hey, could be a 1, could be a 9. Most likely this rounds up to 3.3. This is not perfect. It's not a perfect system, but it tends to increase our amount of accuracy, and it's a great communication tool. When we want to look at finding the density of something, we use mass and volume. So we'll look first at volume. If I had a graduated cylinder, our graduated cylinders allow me to only measure whole numbers of milliliters. So say I put 47 milliliters into a 100 milliliter graduated cylinder. If I pour this into if I pour some of the water into a 10 milliliter graduated cylinder, so I'm going to pour 6.6 milliliters in there. Our 10 milliliter graduated cylinders actually can read that decimal place. So I poured out this 6.6 milliliters. I want to know how much remains in the large graduated cylinder, I'm going to subtract these. So I'm going to do 47 minus 6.6. I'm going to again run into this problem where in reality I don't know what's right here. It could be a 0, it could be a 9, not really sure. So I'm going to subtract this based on what I have, which gives me 40.4. I can't be super confident about this 4 though. So what I actually have to tell people is, I don't really know that decimal place there. So I'm just going to actually call this 40. And I want people to know that it is 40 on the dot, so I put a little decimal place right after it. Again, there may be another decimal place after that 0 or after that decimal, but we don't know what it is. Imagine I wanted to calculate the density of a sample. So I measured its mass to be 4.51, and I measured its volume to be 2.6. Remember, our density formula is mass over volume. If we punch this into your calculator, this is one of those times where you're going to say, okay, look at this big old decimal I get. Then you're going to raise your hand and you're going to say, how many decimal places should I have in my answer? And I think some kids want there to be a set rule that it's always to the 10th or always to the 100th, but in Sig Figs, which actually answers this question for us, we base it on what we plugged into the answer. So this number right here has what we call 3 significant figures, or 3 numbers I'm pretty confident about. This one right here only has 2. So what I have to do in my answer is decide how many significant figures based on my least accurate or least significant number, my number with the least number of significant figures going into it. So this guy only has 2, which means I'm actually only allowed to keep 2 from this number right here. So instead of calling this 1.7346 and on, this just turns into 1.7. And again, that's going to mean grams per milliliter, or grams per centimeter cubed, means a pretty similar thing. So a lot of times you'll just simply be given numbers on paper that you'll have to deal with as well, so it's important to be able to determine how many significant figures a number has. So we got some rules. Rule number 1 is easy, we just covered it. Measurements in the lab. You read all the numbers on the thing that you're using to measure, you don't lie or make any numbers up, and all those numbers are significant. End of story. So if you read it on a balance, if you read it on a graduated cylinder, it's significant. Rule number 2 is also really easy. If it's not 0, it's significant. So anything 1 through 9 is, automatically a significant figure. Zeros are where it gets complicated. I gave them their whole column in the table because zeros are a little bit tricky. Middle zeros are easy. Middle zeros always count. So this guy right here is what we call a sandwich 0 or a middle 0. He is stuck between 2 other zeros. If you took him out, this would turn 303 into 33. We don't want to do that. So this number right here has 3 sig figs, or 3 significant figures, because that 0 counts, and our non-zero numbers automatically count also. Leading zeros can be a little bit confusing. Anything that is to the left of this number right here does not count. The reason for this is really we could rewrite this number into scientific notation. You would never rewrite this number as, that would look foolish. You wouldn't do that. Instead, you would turn this into 1.23 times 10 to the negative 2. So you want to think about what it would look like if you turned it into scientific notation. Do these zeros matter? Yes, they do. But they're placeholders. Well, the one to the left of the decimal actually really doesn't matter. But this 0 right here is considered to be a placeholder. So really, this number also only has 3 significant figures because we only count those non-zero numbers. Those leading zeros do not count. Now, trailing zeros do count. This 0 right here is a 0. Okay, so this 0 is actually put there because this is 23.30 milliliters. Not 23.35, not 23.32. We know that's a 0. I think this rule kind of bothers kids. Remember, this is a communication tool, not a mathematical rule. So that's really, people understand that to be a significant figure so that they're able to communicate numbers, not because there's some mathematically special reason that that should count. So this number actually has 4 sig figs. Now, a really confusing thing is if you want to say you have 230 of something kind of exactly, this number right here is actually only showing 2 sig figs, whereas this number shows 3 sig figs. This is a very confusing rule, and probably one that you're not likely to be tested on, but kind of an important one to understand. So once you actually put this decimal here, that clearly tells people that this is 230, and that number right there shouldn't be anything else, but you do want it to count as a significant figure. So this number does have 3 sig figs, whereas this one only has 2. If you're good at something in scientific notation, they all count. Leading zeros, you don't have to worry about any of the rules we just talked about, they automatically count. 2 sig figs. This is written in incorrect scientific notation. That's 3 sig figs. And we'll talk a little bit more about scientific notation separately. Exact numbers have unlimited significant figures. So in a typical class, I'm going to say there's 22 students. In a class that has 22 students in it, we could actually kind of lie and say, well, it's not really lying. This is the same as 22. We don't really have any half people. We don't have 0.7 of a person in here. So we can be pretty confident that when we plug this number in, it should not limit the significant figures in our answer. So if I had a hunk of gold and I was going to be really nice, divide it by everybody in the room. So if I have 233.567 grams of gold and I want to divide it by the 22 people in the room, when I get my answer, I want to make sure that looking at this, you might think, oh, I got 2 sig figs there, so I can only show 2 in my answer. But really, I can add as many zeros to this as I want. Those are trailing zeros to count. So my number of significant figures is actually going to be based on this not exact number on the top. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So if I wanted to round this to the proper number of significant figures and tell you how much gold you were going to get, it would be just over 10.5 grams. You can look up the exchange rate and find out how rich I made you on Google. We will talk about those mathematical rules separately. So a little exercise here first. Take a moment, look at each of these, figure out how many significant figures you have. You can pause the video for a minute, and I'll pull up the answers in just a moment. So 60 seconds is a trick. It's unlimited. Even though technically, if you go back to earth science, you can find out time doesn't break down that perfectly, but for our purposes, there are exactly 60 seconds in a minute. We have 4 significant figures. We have a trailing 0 there, so that counts. That's a measurement of a number of grams coming from a triple or a balance of some kind. So those all count, and that is 4 significant figures. My next number, where I'm drinking a bunch of water, just over a liter, those all count as significant figures. We've got sandwich zeros, we've got a trailing 0. Every single one of them counts. Again, in both of these, this 0 is kind of strange, but it means we actually know that should be a 0, not some other number. Her hair is almost 350 millimeters long. Gives me 2 sig figs. If you're looking at this and you're like, but what if it is exactly 350 millimeters long? You'd actually have to throw that decimal right there, and that would turn that into being 3 sig figs. Without that decimal, only the 3 and the 5 count. Number 5, that road is 0.0950 meters in length. 3 sig figs on this one. So my leading zeros over here do not count. My 9 and my 5 count, and my trailing 0 counts. You also have to be able to round to a specific number of significant figures. So for each of these, what you're going to do is you need 3 sig figs in each one. You could round to a different number of sig figs depending on what you need to do. This is just an exercise to practice that rounding. So in number 1, we know we got to keep the 9 and the 8, okay? So those are going to be our 3 sig figs right there. Because the number following the 4 is larger than 5, you follow your regular rounding rules, and this is going to round liters. I want 3 significant figures in my next one. My zeros over here, remember, those are all leading zeros, so they don't count. So I start at the 7. I need to keep all those numbers right there. You can opt to write this one in scientific notation if you find that easier. So we have 0.00763. If you want to show that in scientific notation, it'd be 7.63 times 10 to the negative 4. So we still have those 3 sig figs there. Try the next couple of them. Pause the video for a moment, and I'll put up the answers in just a second. So number 3 with 3 sig figs, you do have to show that decimal, that 0 after the decimal. If you show just this, you are not showing 3 sig figs. You're only showing 2. So you do have to have that trailing 0. 12.2, so we round up because of that 7. And this one's kind of an interesting one because you're actually getting a lot of arguments about this every year. You are just under 5, under that being a 5 right there. We need to keep the 1, the 7, and the 6. So because this is a 4 right here, that actually rounds down, and this is 1,760 with no decimal place. If you were to do this, all of a sudden you get 4 sig figs. You do not want that decimal place there. If you, you might have the temptation to do this. That is 4 sig figs. You can't do that. And you really don't want to round this up because technically that is below 5. So you want to keep that rounded down. Rules when you're adding and subtracting. Rules of adding and subtracting, it's based on the number of decimal places you have. Decimals don't move much in adding and subtracting. So sometimes I like to actually line these right up so I can see where those decimal places fall. You can actually do the math on your calculator if you want, or you can do it on paper. What we run into is that this little space right here is our big fat question mark. So we don't really know for sure that that's definitely a 1. So when you calculate this, you get 22.959. We can't actually be completely sure that this is a 9. It's going to cause us to round that guy up right there and get 22.96. The rule is the same when we're adding. We line up those decimal places. It doesn't actually matter how many significant figures the number has overall. It just matters how many decimal places we have when we're adding or subtracting. So when we add these guys together, oops. Sorry about that. Oh, sorry, I dropped a number there. Wondering why that was looking a little bit weird. Sorry, 67.352, 2.90, oops, 601.2. So we're actually going to be quite limited in this just because our large number only has 1 decimal place. So when you add these together, you get 671.452. We have a lot of question marks in this one, so we really can't keep either of these guys. Because that's a 5, we will round that up, and we will get 671.5. For multiplication and division, the rule is a little bit different. Decimal places can move a lot in multiplication and division, so we actually base this on the number of significant figures. So if you punch each of these into your calculators, 23.641 times 2.4, you're going to get a number with a decent amount of decimal places in it. We're going to look back at our 2 numbers that we have going into this. We have 1, 2, 3, 4, 5 sig figs and 2 sig figs. We are limited to the one with the least amount of significant figures. So I actually have to round this to 57. I can't keep any of those decimal places. This is a little bit different because we have decimal places in both of the answers we were or in both of the numbers we were multiplying, but it's based more on significant figures since decimal places are able to move in this type of operation. The next one, we're dividing 500 divided by 32.5. We have a lot of decimals here. So we're going to look back on our 2 answers, or on our 2 numbers that we were dividing. 1, 2, 3, 4. 1, 2, 3. So we're limited to 3 significant figures. So we're going to want to keep these and round this to 15.4. So take a moment, I'll pause the video and see if you can figure out the answers to these with the proper number of significant figures. Since 19 has no decimal places, we are unable to give any decimal places in this answer, but we can keep all of the numbers to the left of the decimal. When we look back on our numbers over here, we have 4 sig figs, 3 sig figs, and 4 sig figs. So we're allowed to have 3 in our answer. Number 3, we are limited to 1 decimal place, so that guy right there. And in number 4, we have 1, 2, 3, 4, 5 sig figs, 1, 2, 3 sig figs. Remember, it's a leading 0, it does not count. So our answer needs to have 3